morning, good afternoon, wherever you may be in your day. I hope you're having an awesome one, and this will make it awesomer, guaranteed, because we are going to balance chemical reactions, a nice focused block of work. Don't worry, you didn't lose me. All right, so let's do a couple things first before we actually balance, and let's just talk about why we need to balance. Well, the first law of thermodynamics states, loosely, that we cannot create or destroy energy or matter. Now, we can convert one into the other and vice versa, and different types of matter and different types of energy, but we can't actually destroy it or create it. And this comes into balancing. So whatever we have before a reaction occurs, as far as atoms and protons and electrons and neutrons, we need the same pile of stuff, matter, at the end of the reaction on the product side. So if we take something that seems quite simple, calcium metal reacts with oxygen gas to produce calcium oxide solid or salt, and we look at this a little bit more closely, we'll see there's actually a problem here. So, in all of these things, the first thing we need to do is find that arrow and really use that as a divided by line. So we have before and after, or reactants and products. So if I look at my reaction here, again, if there's nothing written there, we assume there's a 1. And this is 1 of everything that follows until we get to a plus sign or an arrow. So we have 1 calcium unit. Again, an implied 1 here. So I have 1 calcium atom on the left-hand side, also known as the reactant side. If I look at oxygen, once again, implied 1 of everything that follows. And we can see here that in each of these oxygen molecules, we have 2 atoms. 2 atoms times 1 gives me 2 oxygens on the reactant side. Now if I go to the product side, again we have 1 unit, and we have 1 calcium and 1 oxygen. And you can see that this violates the first law of thermodynamics, or the conservation of mass, in that we do not have the same amount of oxygens at the beginning as we do at the end. Now there's ways to alleviate this, and you could say, well, we're missing oxygen, so we need more on the product side. So I'll put a 2 here, and that'll give me 2 calciums. Oh, sorry. This will give me 2 calciums and 2 oxygens, so the oxygen's good. Now I need more calcium, so I'll put a 2 here, and I'm all balanced. And I know this is a method that's used, from what I can see, the majority of high school teachers teach this method. I actually really don't like this method. I can give you examples where you'll bounce back and forth 20 times before you get to the right ratio. What I would like to do is show you a system that pretty much works first time every time. I'll call it my system. It isn't. But it's going to be the system I use for this class. I didn't create it. It's really just logic. So, first thing, and this causes the most confusion for everyone based off what I just said with that bouncing back and forth. In that system, you assume everything has a 1 in front. We're going to do the opposite. We're going to assume there's a 0 in front of everything. So before we start balancing, I might ask you, how many blank atoms do I have on the left? And you're supposed to say 0. If I say, how many blank atoms do we have on the right? You're going to say 0. All right, you got it. Okay. Then we're going to find the biggest, most atoms, most elements, I don't know, whatever you think looks the most complicated, and we're going to put a 1 in front of it. Doesn't really matter what you pick. If we come to a place where we're stuck, you may have to start all over. And to minimize that, usually if you take the thing with the most elements and atoms, that will minimize the chances that you'll have to do that. Tally up what we have. It's always good to keep a running tally till you get really used to this. And then find any other element that we have in our tally that shows up in one and only one other place. Then balance that. For those of you that are not strong in math, it's the number of atoms we need to balance divided by the number of atoms in the formula unit. And that will always be the right fraction. You can put that out front. And then if you really don't like fractions, you can multiply through by the bottom of the fraction all the way through. Just remember, anything with the 0, anything times 0 is still 0. Multiply all the way through and you get rid of the fraction. And sometimes you might have to do this more than once, and I'll show you in some examples. And if you get to a point where you can't do number 4, where there are no elements that only show up in one place, they show up in 2 places, so you can't balance them, then you picked the wrong thing to start with, and you got to try another one, which is no big deal, but you do have to start over. All right, so let's take a fairly straightforward example. S8, sulfur plus oxygen gives me sulfur dioxide. All right. So right now, how many sulfur atoms do I have on the reactant side? Good, none. How many do I have on the product side? Good, none. How many oxygen? None, 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 none. All right, we get 0 of everything. Now we want to take the biggest, scariest looking thing and put a 1 in front of it. Some of you might say S8. Some of you might say SO2. I'll do it both ways. Let's say S8 has the most atoms. So I put a 1 in front of this. Now we want to tally up what we have. We have 8 sulfur atoms. That's easy enough. And now I want to look in the places where I have openings, where I haven't put a number yet, and see how many different places sulfur shows up. I do this creature habit. I just work left to right on all these. I don't use a lot of thought. Sulfur, nope, yup, it's only in one place. That's fantastic. How many do I need? I need 8. They come in groups of how many sulfurs in a pot? 1. So 8 over 1, or, just to show you that method. I know that 8 divided by 1 is not really high-level math, but we'd have 8 there. Do your tally again. We have 8 sulfurs, and 8 times 2, 16 oxygens. So this is good. Sulfurs are balanced. I'll cross that out. I have 16 oxygens. They only show up in one other opening, so we can balance that. We need 16. They come in groups of 2. 16 over 2 gives me 8 oxygens. Redo my tally. 16 oxygens, boom, boom. Everything's kosher, everything's good. We are done. Pat yourself on the back, high five yourself, whatever you would like to do. All right, let me show you what it looks like. We do it a slightly different way. What if I decided that that didn't look too bad? It's only got 1 capital letter. That's got 2 capital letters. Whoa! So maybe I put the 1 over here. All right. So we have 1 sulfur, 2 oxygens. And I look and I go, okay, let's just work. I got 2 oxygens here, that's fine. I need 2, they come in sets of 2. 2 divided by 2 is 1. I'm rolling along, redo my tally, 2 oxygens, boom, boom. And now I have my sulfur. I need 1, they come in sets of 8. So 1 divided by 8. Now, technically this is correct. This is a balanced reaction. More formally, when we balance reactions, it's the lowest ratio of whole numbers to balance the atoms. So that's not a whole number, so to get rid of the 8, we have to multiply everything by 8. So we get S8 plus 8O2 yields 8SO2. And if you look at your notes, which I'm sure you guys are all good students, you've been taking notes as we've been going. If you look at your notes, you'll see this is exactly what we got with the other method. And if you had done this before the oxygens, when you multiply through by 8, that would still just be a blank. And you could do the same thing. So 8 times 2 is 16 oxygens, 16 over 2, and I get my 8. So 3 different ways of tackling the same problem. Just to point out that it's not critical what you start with. Just follow the logic train. Okay. Let's take our car engine. Let's throw some octane, light it up, get CO2 and water out the tailpipe. All right, I think it's pretty obvious what the largest atom or molecule is up here. The largest molecule is this guy up here up front. So let's put a 1 in front, do our tally, 8 carbons, 18 hydrogens, and look and see. So carbon is not here, it is here, not here, it's only in one place, we can balance it. We need, don't move on me now, we need 8. They come in sets of 1. We're just looking at the atom we're balancing, so 8 divided by 1 is 8. This gives me 8 carbons and 16 oxygens. Now I could try to do oxygen, but here's an opening with oxygen, here's an opening with oxygen. So we can't do oxygen yet. But luckily we can do hydrogen. So I have 18, so I need 18 more over here. 18 divided by 2 is 9. Let's do our tally. 18 H's, 9 oxygens, so that cancels out. And now, remember, when you're doing this, everything needs to balance. So how many oxygens are there on this side? There's 25. They come in sets of 2, so I will put 25 over 2 here for the balancing, and we've balanced our equation. So this is 25 oxygens, and everything here is balanced. Now, we still need to get rid of the fraction. So multiply this whole thing by 2. You get 2 octane plus 25 oxygens yields 16 carbon dioxide and 18 water molecules, or moles, depending on your unit of choice. And that would be a balanced equation, or reaction. Oh, both. Don't fall on me. I'll do one more. Hopefully you're getting the hang of this. Here's one where you could start in the wrong place. What would that look like? What would that look like? Let's say I started here. Just want you to know what happens if you start in the wrong place. If I start here, pretty easy. I got 2 oxygens. I only have one choice, so oxygen, no, 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 yes. So that's good. We need 2. They come in sets of 1. 2 over 1 is 2. That gives me 4 hydrogens and 2 oxygens. So the oxygens are balanced. And now we want to go to balance the hydrogens, but we notice what? 2 openings. And there's no way to balance this. Actually, 3 openings. There's no way to balance this. We've hit a dead end. If this is the case, we got to start all over. So, oh well. If you got a piece of paper, ball it up, shoot it at the trash can, see if you can make it. Otherwise, use your eraser, get right back to work like we're going to be here. Okay, so let's pick somewhere else to start. I don't know. Usually the most elements is a decent place, so let's try this one. 1 hydrogen, 1 carbon, 1 nitrogen. So, I like to work left to right. Hydrogen, 1 spot, 2 spot, that's out, skip. Carbon, 1 spot, no, no, and no. Hey, we can do carbon. We need 1. They come in sets of 1. 1 divided by 1 is 1. Redo our tally. Alright, carbon's out. And hydrogen's still a problem. We got 2 openings, so hopefully this other element will help us out. Nitrogen is yes, no, no. So that's excellent. It's only in one place. We need 1. Comes in sets of 1, so the number we need over the unit, so 1 over 1 is 1. 1 nitrogen, 3 hydrogens. Boom and boom. And I have, once again, no, we're good. We can now do the hydrogens. So if we look at the left-hand side, we have a grand total of 7 hydrogen atoms. If we look at the right-hand side, we already have 1. How many do we need to balance? We need 6 more. They come in sets of 2. What we need over what they come in, so 6 over 2 gives me 3. And you can see we've now balanced out the hydrogen. We have 3 oxygens. They come in sets of 2, so this is 3 halves. Multiply this whole thing by 2, and we get 2 methanes plus 2 ammonia plus 3 oxygen yields 2 HCNs and 6 waters. You know, it's also not a terrible idea at the very end to make sure that you haven't lost anything, so just add it up. All right, I got 2 carbons, 8 hydrogens, 2 nitrogens, another 6 hydrogens, 6 oxygens. Over here I got 2 hydrogens, 2 carbons, 2 nitrogens, another 12 hydrogens, and 6 oxygens. All right, 6 and 6, 2 and 2, 2 and 2, 14 and 14, and it's balanced. It's really a shame if you miss one of these problems because you can check and see if you have the same things on the left and the right. With that, I hope this was probably one more example than you really need to see, but hopefully you're very comfortable using this method and balancing reactions, and hopefully you see the utility of basically just going through one chain of logic. You don't have to bounce back and forth until you randomly land on a balancing place. Simple reactions, that works well. Complicated reactions works very poorly. So, hope you enjoyed this. Have a wonderful day, and look forward to seeing you.